Oh, hi. This is the momentum summative assessment. Start question number 1. A 20 Newton force acts on a body and its momentum changes by 80.0 kilogram meters per second. How long does the force act? Alright, so how long does the force act is probably the biggest clue that we're going to be talking about impulse in this problem. So force times a change in time equals a change in momentum. And these are vector equations. I should maybe ask you to give me a before and after values for the body that has the momentum changing, but let's just go with force times a change in time equals change in momentum. So 20 Newton force times a certain length of time equals a change in momentum. We're given the 20 newtons. This is force. So sorry, force times a change in time equals a change in momentum. We're given the force, 20 newtons, and the change in momentum. So the change in time is equal to 80.0 kilogram meters per second divided by 20 newtons, which is 4 seconds. You can verify these units by reminding yourself that kilogram meters per second and newtons is a kilogram times a meter per second squared. So if I multiply top and bottom by seconds squared, I basically have just seconds left over. So 4 seconds, the answer is going to be B. Okay, let's go next question. A 60 kilogram cosmonaut jumps from her 5,000 kilogram spaceship in order to meet her co-pilot, who is floating at rest a few hundred meters away. If she sails toward him at a speed of 10 meters per second, what is the resulting motion of the ship? So the cool thing about space is that there are no external forces. So if there's no external forces on the system, and let's say the system is spaceship, cosmonaut, and other cosmonaut. This is our system. Then we write conservation of momentum laws, and the force external in a vector way is the change in momentum, but the force external is 0, so we only have that the change in momentum is 0, which means if we break it out that the momentum before minus the momentum after equals 0, which means that the final momentum equals the initial momentum. Okay, so we can do this. The initial momentum of the whole system is 0 because nobody's moving initially, which means that that was final momentum. Initial momentum is 0, which means that we have final momentum is 0. So if I have, this is before, let's be sure and label these pictures. This is the before picture. The after picture has cosmonaut moving towards their comrade, let's say, and spaceship moving other way. Then we know that 60 kilogram cosmonaut moving at 10 meters per second must equal 5,000 kilogram spaceship moving the opposite direction at what speed? So since I know the directions, I have to make it equal to 0. I could either put it on one side of the equation or I could just put them equal. Let's just say that 5,000 kilograms times V equals 60 kilograms times 10 meters per second. Or V equals 600 kilogram meters per second divided by 5,000. I'm okay with dividing by such a big number because I realize that the spaceship, it has a mass much greater than the cosmonaut, and so I'm okay with this being 6/50 meters per second. Or, let me divide that out for you here. Low tech, 6 divided by 50, 0.12 meters per second. If you've learned anything in this chapter, please remember that because of action and reaction, partially, but also because of the laws of the universe, the things have effects on each other. All right, so question number 3. There's only 3 questions, and the 4th one is extra credit, so let's talk about this question. I don't want the camera to get in the way. Okay. Conservation of linear momentum. 2 blocks on a frictionless air table slide directly towards each other. The first traveling east, so remember north, south, east, and west. First one traveling, let's see, here's a block. Let's say this line here is the frictionless table, so it's going east, has a momentum now, mass times velocity of 10.0 kilograms meters per second. The second one traveling west has a momentum of 15.0 kilograms meters per second. So that one's going this way. Taking east to be positive, what is the initial momentum of each block? What is the total momentum of the 2 blocks before the collision? And what is the total momentum of the 2 blocks after the collision? Okay, so for part A, the initial momentum of each block. So for, let's say this is block 1, and this is block 2. So for block 1, the initial momentum is given to us as 10.0 kilogram meters per second. And for block 2, the initial momentum is 15.0 kilogram meters per second. And let's see, we reckon this way as positive. So we'd actually say that number 2 is minus 15 kilogram meters per second. That means that B, the total momentum of the blocks, is the sum of the two, 10 kilogram meters per second minus 15.0 kilogram meters per second, which equals minus 5 kilogram meters per second. That's good. Let's put a square around these answers here. So that's the total momentum of the 2 blocks before collision. And then after collision, part C, we're going to say that because momentum is conserved, there's no external force. Remember our condition for momentum conservation, there's no force external. And so because there's no force external, which is the only way you can get a change in momentum, we've got a change in momentum which equals 0. So total momentum before equals momentum after. So then, total momentum before equals total momentum after, we have to have that same total momentum in the system, so minus 5 kilograms meters per second. I think you should convince yourself that what's going to happen after is block 1 is going to bounce off and go 15 kilogram meters per second, and then block 2 is going to bounce off and go 10 kilogram meters per second. So in a sense, they're going to trade their velocities. And that's it.